When we talk about climate change, it's so easy to get bogged down, right? To feel a bit overwhelmed. Well, today we're going to flip the script. We're diving into a refreshingly optimistic take that's all about engineering, not just identifying problems, but actually building creative, tangible solutions. This quote, man, it just perfectly sets the tone for what we're talking about today. It's all about shifting our mindset away from despair and asking a much more powerful question. Okay, so what can we do? The focus isn't on what we failed to do, but on what we can build right now. Okay, so here's our game plan for this explainer. First, we'll frame the big challenge. Then, we'll zoom in on how we can protect our planet's massive ice sheets. From there, we're going to shrink all the way down to the molecular level and look at grabbing carbon from the air. And finally, we'll tackle the most complicated system of all, us, the human factor, before tying it all together. Right, so the core question is simple, but honestly, it's pretty profound. How do we apply a design and build mentality to move the needle on one of the biggest challenges of our era? To get our heads around this, let's start big. I mean, really big. We're heading to the world's ice sheets, which are ground zero in the climate story. But here's the thing. To find a solution, you first have to understand that the problem isn't the same everywhere. So you might think ice is ice, right? But what's so fascinating is that Greenland and Antarctica are facing totally different threats. In Greenland, the big problem is on the surface. You get these meltwater lakes that drain down to the bedrock, acting like a lubricant that just speeds up the glaciers slide into the ocean. But in West Antarctica, the enemy is coming from below. Warm, salty ocean water is literally sneaking under the ice, melting it from the bottom up. And that leads us to a really cool engineering puzzle. I mean, you can't just go and build a 3-kilometer deep concrete wall to hold back a glacier. The forces are just mind-boggling. It's a total non-starter. So if a solid barrier is out, what do you do? Well, if you can't build a solid barrier, you build a fluid one. And this idea is just so elegant. A bubble curtain. It is exactly what it sounds like, a wall of bubbles. It's not trying to be a dam. It's a subtle barrier designed to disrupt the flow of that warm water and stop it from reaching the ice. And here's the nuts and bolts of it. You lay a pipe with holes in it on the seafloor, you pump air through it, and voila, you get this rising curtain of bubbles. It's a clever way to gently nudge a massive natural system in the right direction without some huge destructive project. All right, so we've gone big. Now let's switch scales completely. We're going to zoom all the way down from these vast frozen landscapes to the invisible world of molecules in the very air we're all breathing. The challenge here? Pulling out the CO2 that's already up there. And that's where something called direct air capture, or DAC, comes into play. You can basically think of it as an artificial forest. But instead of leaves, these things use special chemical filters to literally grab CO2 molecules right out of the air, just on a massive industrial scale. Okay, but here's a number that might make you scratch your head. When you hear that a leading DAC system is only about 5.3% efficient, your first reaction is probably, wait, that's terrible. Why would we even bother? It sounds incredibly wasteful, but that number doesn't tell the whole story. See, here's the crucial insight. Perfect efficiency isn't actually the goal. The goal is being cost-effective. So if you can build these systems really, really cheaply, and then you run them using renewable energy when there's an oversupply on the grid, when that power is essentially free, then suddenly that low efficiency number doesn't matter nearly as much. So we've talked ice, we've talked air. But now we come to the trickiest, most complex piece of the entire puzzle. Because you can design the most brilliant machine in the world, but if nobody wants to build it, or fund it, or live next to it, it's just a fancy paperweight. And this quote just says it all, doesn't it? History is absolutely littered with technically amazing ideas that just failed. They failed because of social opposition or political roadblocks. Understanding what people value is just as critical as getting the physics right. So what do people actually care about when it comes to these big projects? Well, a study dug into this, asking all kinds of stakeholders to choose between different climate solutions. And the results are pretty eye-opening. You'd think cost would be number one, right? Nope. Look at this. The single most important factor was resource impacts. How much land will it use? How much water? That's what people wanted to know first and foremost. And get this. This is the real kicker. The group that cared the least about the price tag was the private sector. The theory is that they just assume the cost will come down over time as the tech gets better, so they're way more focused on other things like land use and long-term stability. It just completely flips the script on what we assume corporations care about. It's not just what we do, but how we talk about it that matters so much, which leads to another fascinating study that looked at something simple: pictures. How can a single image completely change someone's mind about a new technology? Well, the answer is a lot, and in completely opposite ways. Check this out. When environmental groups were shown an emotional, nature-focused image, their support for the tech went up. But, and this is wild, when people from the private sector saw that exact same image, their support went down. The picture that inspired one group created skepticism in the other. It's just a perfect reminder that one message does not fit all. So where does this all leave us? What's the big takeaway? It's that we can't think about these things in silos anymore. Protecting ice, capturing carbon, and understanding people, they're not separate challenges. They're all deeply, deeply interconnected. Which brings us to this new blueprint, really, built on 3 essential pillars. First, you need the big physical interventions, like the bubble curtain. Second, you need the molecular-level chemical processes, like direct air capture. And third, and this might be the most important of all, you need deep social engagement to make sure these incredible ideas actually get off the drawing board and into the real world. And that leaves us with one final thought to chew on. As we look to the future, what's the real engineering challenge here? Is it building the machine? Or is it building the human consensus that allows the machine to exist in the first place? The truth, of course, is that it's got to be both. Thanks for joining me.